Hello everyone and welcome to Network Playroom. This is the 8th video in the Christmas calendar series, and today we're going to talk about the spanning tree protocol. I briefly introduced spanning tree yesterday when I discussed loop prevention at layer 2 and layer 3. To review the subject quickly, the purpose of spanning tree is to logically block redundant links to prevent loops from happening. Unlike layer 3 packets, which have the TTL field built into the IP protocol as a last resort to stop packets from circulating in the network infinitely, layer 2 frames or Ethernet frames have no such built-in mechanism. That's the job of spanning tree protocol. So actually, a lot of the content for this video is from my blog I wrote a while ago. I'll leave a link in the description if you're interested in reading it. But let's get started. So how does spanning tree decide which links to block? This is a multi-step process which involves 3 main operations, which I've written down on the screen here. So number 1, determine the root switch. Number 2, find the best path to the root switch. And number 3, block redundant links. And we're going to look at each step in more detail shortly. So the key is for all the switches in a layer 2 network to elect a root switch, also referred to as a root bridge, that becomes the focal point in the network. And STP uses deterministic rules to decide which ports to block to break loops and which ports to put in the forwarding state. And all decisions are made from the perspective of the root switch. So since the root switch is central in the network, its placement is very important. An administrator can manually control the selection of the root switch and let the switches automatically run through the process and decide among themselves. However, suboptimal forwarding paths can result as a consequence of the latter. It is recommended that the administrator plan the placement of the root switch prior to deployment and modify the configuration accordingly. Okay, so the switches exchange information for use of the root switch selection and subsequent configuration in the network using a special frame type called the Bridge Protocol Data Unit, or PBDU for short. So PBDU. Keep this in mind for later use. So the STP calculation is based on comparing PBDUs. A switch simply compares the parameters of a received PBDU against the information saved in its own PBDU and makes decisions accordingly. And in STP, lower is better. And we'll look at the PBDU in more detail at another time. But for now, it's enough to know that it's the language of love between the switches, and spanning tree is based on the exchange of PBDUs. All right, but now let's look at number 1, or selecting the root switch. So the root switch is determined by the bridge ID. And the bridge ID consists of a configurable priority value and the MAC address of the switch. And the switch with the lowest bridge ID is selected as the root switch. And the bridge priority is 32,768 by default. So let's write that down here. Default bridge priority is 32,768. You don't necessarily need to memorize that, but it's good to know that's the default value. So if the bridge priorities are equal, the lowest MAC address is preferred. So basically, by default, the network chooses the oldest switch as the root switch because they usually have the lowest MAC addresses. This is why it's so important for the administrator to control the selection and placement of the root switch. You don't want your oldest and most likely the weakest switch to be the root switch in your network. So I mentioned that the bridge priority is 32,768 by default. So why does it say 32,769 in the diagram? So here I've listed the bridge IDs for each switch, and this part is the priority, and the remaining part is the MAC address of the switch. Like this. So why does it say 32,769 here, when I've just stated that the default priority is one less? Well, the reason is that the switches are using what is called the system ID extension. And STP actually calculates the topology on a per VLAN basis, so the system ID extension is used to create a unique bridge ID for each VLAN. Hence, there's no need to use a different MAC address to identify each instance. So let's look at a diagram of that. But first, let me get rid of this information, because I'm gonna open up one of the hidden layers now. So I'm looking for this one. So here you can see that the bridge priority actually consists, the bridge ID consists of three parts. So the first part is the priority, and then we have the system ID extension, which holds the VLAN ID, and then the MAC address. So now the bridge priority by default is 32,768, and we're looking at VLAN number 1, so this would be 1. And that's why. So it's the priority plus the VLAN ID, which is equal to 32,769. Okay, but now that we know that, which switch will become the root switch? So we know that the priority is the same for each switch. So we must now look at the MAC addresses. So what we have here is switch A with a MAC address of 00900Z294720. Then switch B, we have 00E0 B044 B69D, and then finally switch C, we have 0090 2B C9, and then 313A. So the MAC addresses are simply compared from left to right until a differentiating value is found. So here we can see all start with 00, but then switch B has E here, which is bigger or higher than 9, so we can completely discard switch B. It's not going to be the root switch. So now the comparison is between switch A and switch C. And you can see here, we'll have to compare this value, and on switch A, it's lower, so the winner is switch A. Switch A will become the root switch. All right, let's get rid of this information as well. Actually, let me get rid of the whole layer here. And then let's hide this one. So we should be able to verify the information in this output. So as you can see here, we're on switch A and we're looking at the show spanning tree output. And on this line, it does state that this bridge is the root. Now, similarly, if we look at the information on switch B, it is saying that the root bridge is the switch with this priority and MAC address. And now, as you can see, that is the MAC address of switch A. So the output matches. All right, but next let's talk about number 2, finding the best path to the root switch. So after the switches have agreed on who is elected as the root switch, they start calculating the best path towards it. Now there can only be one such path, and it is the one with the lowest cost. And the path cost is inversely proportional to the bandwidth of the link, and that is the higher the bandwidth, the lower and more preferred the cost. So the best path selection process has other tiebreakers if there are multiple equal cost paths, but we'll ignore those for now. So all of the links between the switches are fast Ethernet interfaces, as you can see here. So their default cost is 19. And actually, let me get rid of this again. We're gonna add another output here. Where is it? So here's the table I was looking for. So this one lists the default costs for different link speeds. So fast Ethernet is 100 megs. So the default cost is 19. So let me write that down here. So let's look at switch B, for example. So it has 2 paths to reach the root switch. Either using the directly connected link with a cost of 19 right here, or go through switch C with a cost of 38. So go through here, and then the cost would be 19 plus 19, and that's 38. So of course, this path is the least cost path to the root switch. So FA0/1 becomes the root port because of the lower cost, and it is put in the forwarding state. And the root port, or RP, is simply the least cost path to reach the root switch, and there must be exactly one root port per each non-root switch. So this is the root port for this switch, and similarly, this would be the root port for switch C. So root port. All right, and then let's look at number 3. Oh, sorry, before I do that, let me show you the root ports. So here we can verify the information. So we're looking at the show spanning tree output again on switch B. You can see that FA0/1 is indeed the root port, and it is in the forwarding state, and the cost is 19. And the same is true for switch C. FA0/1 is the root port, it's forwarding, and the cost is 19. Here we're looking at switch C. So now let's move on to number 3, which is blocking redundant links. So once the root port has been selected, the switch must decide which remaining ports are put in the forwarding state and which are blocked. And there must be exactly one forwarding port in each segment called the designated port. And in order to become the designated port, the switch must send superior PPDUs on that segment. And to determine the superior PPDU, the PPDUs are compared in the following sequence, looking for the first occurrence of lower value. So we're looking at root bridge ID, root path cost, the sender bridge ID, and sender port ID. So again, let me make some space here. Let's remove some of this. We'll leave the other information for now. Let's hide this output and this output. Okay, so what we need to decide is that which interface from these two are going to block, and the other one is going to be a designated port. So to determine that, there are 4 different components that we need to look at. And they are the root bridge ID, then root path cost, and then sender bridge ID, and then finally sender port ID. Oh, that doesn't look very good. Sender port ID. So these are compared in sequence and looking for the first occurrence of a lower value. So number 1, 2, 3, 4. So let's compare each component between switch B and switch C. So first, the root bridge ID. So both switch B and switch C are advertising the same root switch, so the root bridge ID is equal. They're both advertising switch A. So this one is going to be equal, so we have to move on to the next step. So the root path cost. So both switches have the same root path cost, which is 19, right here. So both switches can reach the root switch A with a cost of 19. So this is also equal. So we must move on to the next step, which is the sender bridge ID. So the switches are still tied. So the sender bridge ID must be evaluated to break the tie. And since the bridge ID of switch C is lower than that of switch B, as you can see here, so this one is lower than this one. So therefore, this port FA0/2 on switch C will become the designated port for that segment, and FA0/2 on switch B will be put in the blocking state. So this one, let's see. So this is going to be the designated port, and this is going to be blocking. So, okay, let's see that on another topology diagram. So let me get rid of this information again and hide this one and open up this one. So as you can see now, the blocking port is indicated with this orange link status. So that means that this interface is blocking, and this one is the designated port, and these two are root ports. And by the way, all interfaces on the root switch itself, switch A, are designated and forwarding. So these would be designated ports as well. Okay, but next let's examine how data is forwarded in the resulting spanning tree topology. So let's add two PCs in the topology and ping between them. So again, let me get rid of some of the information here and then change the topology to this one now. So we've added PC0 and PC1 with the IP addresses from the 192.168.1.0/24 network. So this one is So this one is .10 and this one is .11 in the 192.168.1.0/24 network. So we want to ping between them. So what path does the packet take? So looking at the topology, you might mistakenly assume that the traffic is forwarded through the directly connected link between switch B and switch C because that is the shortest path between the PCs. So you might think that the packets are going through this link. And yes, from the PC's perspective, that would be correct. It is the shortest path between them. However, the underlying layer 2 topology is built from the perspective of the root switch. So now it is more evident how the placement of the root switch dictates packet forwarding. So because of spanning tree protocol, from the end host communication perspective, the underlying layer 2 topology is effectively the same as if the link between switch B and switch C didn't exist. And user traffic is not allowed to pass on the block link, but control plane messaging like sending PPDU still occurs. So let's look at that now. Again, let me remove this information and then open up the final topology. So here we can see this is actually PC0, and we're pinging PC1. It's a .11 address, and there's the reply. So the ping is successful. So now you can see here in the below output on switch B, if we look at the MAC address table. So here's the MAC address of PC1, as you can see here. And it was actually learned on this interface. So this is the resulting topology, spanning tree topology. So this is something important to keep in mind. So although we had the link here, that doesn't mean that it is used to forward packets. It's not used to forward normal data traffic. So you might look at a diagram or a network and think that packets are flowing in this direction, but it's not true. You need to know what the spanning tree topology is and whether some links are blocked. But yeah, that's it for this video. This was a brief introduction into spanning tree protocol. We'll surely look at other spanning tree topics in future videos, so stay tuned for that. And I'd like to thank you for watching, and I'll see you in the next video.